the objectives up there, and it is describe the types of properties of ionizing radiation, and then outcomes-wise, describe radioactive decay, describe the type of nuclear radiation, and then explain the processes of alpha decay and beta decay. So there's a few keywords for you again there. We've got alpha particle, beta particle, gamma ray, and becquerel as well. Now there's a quick starter question for you there. You might have seen the first lesson, you might not, it doesn't really matter. The starter task is just to name the 3 subatomic particles and describe their relative charges and mass. So again, don't spend more than 60 seconds on that. Write down what you can from memory, and then pause the video and I'll go through that in a second. Okay, so the 3 subatomic particles, we've got protons and we've got neutrons. They both reside within the nucleus of the atom. Sometimes they're called nucleons together. And then we've got electrons which orbit around the nucleus in shells. Their relative charges and masses. We'll do the masses first. So a mass of a proton is 1, and a mass of a neutron is 1, and the mass of an electron is almost 0, comparatively. And then the charges, a proton has a +1 charge, as in it's positive by 1. A neutron does not have a charge, it's neutral. And then an electron has a -1 charge, as in it's got 1 negative charge on it. Right, let's go straight into it then. Right, so if an atom gains or loses an electron, it becomes an ion. Hopefully you've encountered ions in another lesson before, but they play a massive part of the radiation topic, so it's good to get familiar with what an ion is. So let's do that. So we've got up here a neutral atom. Like, you could pick any atom on the periodic table, it doesn't matter. If it gains or loses electrons, it will no longer be called an atom. It becomes an ion. There's 2 different types of ion, and I'll be honest with you, you don't need to know whether it's a cation or an anion, you can see here, for this topic. You do in other topics, especially in chemistry, but just for now, all I want you to know is if a neutral atom loses electrons or a neutral atom gains electrons, it becomes an ion. Whether it's a cation or an ion, it doesn't make a difference. You just need to know that if an atom that is neutral gains or loses electrons, it becomes an ion. Okay then, so bearing this in mind, what do you think ionizing radiation is? Okay, so it's just radiation that can cause atoms to lose or gain electrons. So if ionizing radiation was to hit an atom, as in something that is neutral, it could hit it and supply enough energy for an electron to be lost from that atom that was initially neutral. But if it loses an electron, now it's obviously had a change in charge. It's no longer neutral. It's become charged, and therefore it's an ion. Right then, radiation. I've just told you radiation can cause things to become ions, and there's something called ionizing radiation. What actually is radiation in the first place? So all ionizing radiation is a product of unstable atoms, and they're unstable usually because they're massive, they're enormous, and the bigger an atom is, the more energy it's got, and the more energy something's got, the more unstable it becomes. So anything after about lead on the periodic table, we're talking about some seriously big atoms there, and if they're big atoms, they're unstable, and there's a good chance that they'll be radioactive. Okay, so to become stable, they need to emit this energy, and different sources of radiation do this in different ways. So if you've got a really big atom and it's unstable, to become stable, it will give out some energy, and there's a few different ways that could happen. The types of energy it gives out, or in fact, the types of energy is the wrong way to put it. The type of radiation it puts out depends on the substance itself. So different substances, different atoms that are unstable will give out different types of ionizing radiation. There's 3 types, and we're going to go through those in a second. So the types of ionizing radiation then are as follows. We've got alpha radiation, represented by this symbol here. We've got beta radiation or beta radiation, depending on how you want to say it, which is represented by this symbol here. And then we've got gamma radiation, which is represented by this symbol up here. Okay, so alpha, beta, gamma radiation. So let's just have a bit of a quick look at some detail about each one of these types of radiation. I'm going to go through this again in a second and show you a bit of a diagram that makes it easy to understand. So the ice cream van's here. So alpha radiation exists as a particle. Okay, so it's got 2 protons and 2 neutrons. It is incredibly ionizing. Out of these 3, it is the most ionizing. It's got the lowest penetration that we'll get. So don't worry about what any of that means right now. I'm just telling you that that's some of the facts that you need to know. It's a particle. It exists with 2 protons and 2 neutrons stuck together. So it's 4 subatomic particles that get ejected from the nucleus of an unstable atom, and it is really, really ionizing. So if an atom was to get hit by an alpha particle, really good chance it's going to ionize it. Really good chance. But it's got low penetration. Okay, the next one is beta radiation. So this exists as a particle as well. It's usually an electron, I have put this in here though, positron, in case anyone decides they want to do A-level physics, you'll come across positrons then. But a positron is essentially identical to an electron, but it's not got a negative charge. I'm not going to go into any more detail about that because it could cause some confusion. Beta radiation is less ionizing than alpha, but more than gamma. So this kind of sits in between, and we get a bit weird with the descriptions here. We just compare it to the other two rather than giving it many individual details. It's more penetrating than alpha, but less than gamma. So it won't go through as much as gamma radiation can, but it will go through more than alpha radiation can in terms of penetration. And then we've got gamma, which is one of the easiest ones we're going to talk about today, to understand, I should say, because there's not much to it in terms of detail. So it exists as a wave. It is the least ionizing, but it is the most penetrative. So what's all this that I'm going on about? The easiest way to understand this is to, first of all, to see it in a classroom where we'd actually get some radioactive sources out and we'd show you that the different types of radiation and that they can penetrate different substances, some better than others. So let's have a look at that in picture detail. So imagine I started off and I've got a source of alpha radiation, a source of beta radiation, and a source of gamma radiation. You can see all three of them lined up there, and I set them all off in the same direction. I'll put obstacles in the way along the way, and I'm just interested in how far they can go, how far they can travel. So straight away I put paper in the way of these three sources of radiation, and alpha would hit that paper and not be able to penetrate through it. Beta radiation would be able to pass through paper, and gamma radiation would be able to pass through paper. But just stop for a second and just have to think, why do you think alpha cannot get through that paper, but beta and gamma radiation can? Okay, so hopefully you've had a bit of a think about that. The reason alpha radiation or an alpha particle can't get through paper, but beta and gamma can, is a size thing. Think of it a bit like a fishing net. If you've got a fishing net and you go out fishing and the holes in the fishing net are that big, then anything smaller than that will be able to pass through your fishing net. You're only going to catch the big fish. Paper is not particularly dense, and because it's not particularly dense, there's gaps, not that you can physically see with the naked eye, but there are gaps in between the atoms that make up the paper itself. So if you fire an alpha particle at paper, an alpha particle's bloody massive, so it's very likely going to hit that paper and not pass through it. Whereas a beta particle is minuscule in comparison to an alpha particle, so that will very easily pass through the paper because it's not particularly dense. And then gamma, because it doesn't even exist as a particle, it's a wave, can pass through that no problem whatsoever, like it's not even there. So let's set up another obstacle then. One of these is out of the race already. We've got alpha radiation kind of blocked already, but beta and gamma radiation still going strong. So let's move on. If I was to put a piece of aluminium, thin aluminium, in front of the paper, what would happen there was beta radiation would get stopped by the aluminium, and that's because aluminium's denser than the paper, and the beta radiation won't be able to easily pass through it. You might still detect a tiny bit of radiation on the other side. That really depends on the thickness of the aluminium, but it should stop beta radiation. Gamma passes straight through that again. Doesn't care that the aluminium's there, would make practically no difference to it, again, because even though aluminium is a bit denser than paper, we're talking about a wave here. We're not talking about a particle. It's not something that will be blocked by that because it's a wave. Okay, let's have a look at the last obstacle then, so lead. I like this image because most images on the internet, if you look this up, show you lead stopping gamma radiation, and it's simply not true. It is so penetrative, it can still pass through lead, but lead does absorb a fair amount of gamma radiation. So you can see here, some of the gamma radiation has got to the lead and been absorbed by lead, but still a little bit of it's made it through. That's why when we talk about containment chambers for radioactive substances that are emitting gamma radiation, they're surrounded by massive thick layers of lead, really thick layers of concrete, because we need to try and stop that gamma radiation from getting out, because obviously it could cause all sorts of health problems for anyone that's near it and the environment as well, I suppose. So those are the three different types of radiation there and their penetrative powers. That is not to say on that diagram, it doesn't give you any indication realistically of how ionizing they are, but it also kind of does if you think about the sizes of them. If we're talking about how ionizing something is, as in how likely is it that one of these sources of radiation is going to be able to knock off an electron off something else, then alpha's gonna take the prize there because it's massive. So if I was to set up some atoms in front of something that's giving out alpha radiation, and that alpha particle hits one of those atoms, there's a good chance it's going to knock off an electron because the alpha particle is pretty big. A beta particle is smaller, so the chance of it hitting something and being able to knock off an electron is smaller. And obviously a gamma ray, because it's not a particle, dramatically less chance of it ionizing an atom. Okay, so going from top to bottom there, alpha is the least penetrative, gamma is the most, as in it can pass through the most. But then if we're talking about ionization, it reverses. Alpha is the most ionizing. Excuse me, hiccup. Alpha is the most ionizing, but gamma is the least ionizing. I suppose both of those properties, penetration and ionizing ability, are linked to the size or mass of the object as well. So that's an interesting thing to remember. Okay, so there's a big block of text there. I'm going to read it out to you. This is about radioactive decay. So most nuclei are stable, but some are not. An unstable nucleus undergoes radioactive decay to become more stable. It emits radiation as it decays. An atom with an unstable nucleus is called a radioisotope. So later on in later lessons, I might refer to radioisotopes without giving you a definition, because we've talked about it a little bit here. So an atom with an unstable nucleus is called a radioisotope. The activity of a radioisotope is the number of nuclear decays each second. So if I've got a substance that's giving out, let's say alpha particles, just for no reason, it doesn't really matter, and it's giving out a certain number of those, it's decaying, we say, every time it gives out some of that radiation, we can measure that activity in something called becquerels, and you can see the unit there is BQ, or counts per second. 1 becquerel will be 1 count per second, and we can physically measure radioactivity. You've probably seen on TV like a Geiger counter, or it's got about 3 different names. It's called a Geiger counter, or a Geiger-Muller tube, or a Geiger-Muller counter. It's all the same thing. They all just measure how many counts of radiation there are per second, and you'll hear it on TV. It makes like a crackling noise, like as it's just moving around the room, you hear little clicks, and each one of those is a count of radiation that it's detected. And then as it gets near to something that's highly radioactive, it makes lots of clicking noise. Sometimes it sounds like it's buzzing because it's detecting that amount of radiation, a massive amount of radiation. So 1 becquerel is 1 count per second. Radioactivity is a random process, and it's not possible to predict when a nucleus will decay. Well, that's the very nature of randomness, isn't it? If something is random, it's unpredictable. If we increase or decrease the temperature of the nucleus, we still cannot predict when it will decay. Radioactive decay is independent of physical changes, such as changes in temperature. So if I had something and I'm like, oh God, I want this to decay, I want this to give out some radiation, I've got a bus to catch, increasing the temperature is going to make no difference. It's still a random process, and there's basically nothing I can do to control that situation. Right, there's 3 questions there at the bottom that you should be able to answer from either what I've just told you or what's on the board what's on the video at the minute. So if you just pause this video, I'd say like a minute a question. So in like 3 minutes, come back, and I'll go through the answers to those. Okay, so let's crack on with those. So the questions were: the activity of a radioactive source is 150 becquerel. How many counts would be recorded in 20 seconds? Well, we'll go through the answers in a second. I've got the answer on the next slide. But you need to look at this bit. 1 becquerel is 1 count per second, and it's saying 150 becquerel, so that's 150 becquerel. That's 150 counts per second, and it did that 20 seconds, so it's 150 multiplied by 20. What can you say about all the nuclei of elements larger than lead-208? So I've not mentioned that on this bit, but I did mention it early on. The idea of lead-208, the number there, atomic mass, that 208 is the number of protons and neutrons in its nucleus. That's pretty big, and obviously the bigger the nucleus, the more unstable it becomes. So we'll get to the answer there in a second, but that's what you should have been thinking about. And then explain what does random mean with regard to radioactive decay. So that was described in this little section here, and it's all to do with predictability. So these are the answers. So you should have got 150 multiplied by 20 gives you 3,000 counts. And then number 2, after lead-208, the nuclei are unstable and likely to decay, so they're going to be radioactive. And then number 3, it's not possible to predict when the nucleus will decay. So that is just the nature of being random. Like I say, there's unpredictability. Okay, so let's jump on then. So I'm not gonna lie to you, this bit's a bit wordy, but we need to go through it. So I'm going to read it out to you. Feel free to pause it, to look at the diagram, anything like that. And again, if you've got questions, stick them on the Google Classroom, and we'll answer those questions as and when they come up. So in alpha decay, an alpha particle is emitted from the nucleus. So this is a nucleus up here. Now uranium-238, you've probably heard of uranium before, haven't you? It's a radioactive isotope because, well, it's massive. Look at it. Look at how many protons and neutrons it's got. So that is what's leading to this atom, or this nucleus, I should say, being unstable and wanting to give out some radiation to become stable, basically. So an alpha particle is emitted from the nucleus. An alpha particle is a helium nucleus. Now you might be going, well, where's this helium come from? It's a helium nucleus. If you look at it on the periodic table, if you look at the atomic number of helium, you'll see that the atomic number is 2. As in, to be helium, you need 2 protons. Now, if you look at this, it says here that alpha particles have 2 protons and 2 neutrons. So this is emitted, a helium nucleus, because it's emitted two protons, the fact that it's got two neutrons is irrelevant to the substance that it makes, to be honest with you. The proton number is what determines an element. So we've got two protons, so instantly it's helium. The fact that it's got two neutrons makes no difference, but you should know that an alpha particle is made up of 4 subatomic particles, 2 protons, and 2 neutrons. Okay, so uranium splits into thorium and an alpha particle during alpha decay. Now, I remember the first time I went through this, and I was like, my mind was blown. So I've started off with one substance, and it's given out a couple of protons, and because it's now lost a couple of protons, it's actually completely changed the nucleus from one element into another. And if you go and look at the periodic table and look at how many protons uranium's got, and then you take 2 off uranium, off of the uranium's atomic number, and then go and find whatever number that is, you'll find it's thorium, because thorium's got 2 less protons than uranium has. So by giving out this alpha particle, it's actually changed the substance itself. And it's quite interesting later on when we talk about half-life. I've got quite a nice little like animated graph that shows you. If I started off with like 100 nuclei of uranium, for example, and I had 0 nuclei of thorium, you'd see that over time as it decays, it does that. And I end up with 100 nuclei of thorium. It changes from one to the other because it's given out, it's decayed, it's given out all those alpha particles. So when an alpha particle is emitted from a nucleus, the nucleus has got 2 fewer protons. You can see that because it's just farted out that alpha particle containing 2 protons. So the atomic number or the proton number decreases by 2. Oh, that makes sense, doesn't it? If its atomic number was a certain number beforehand and it's just giving out 2 protons, its atomic number is going to reduce by 2. The nucleus also has 2 fewer neutrons, and this gets a bit confusing. It's got 2 fewer neutrons, but the mass number decreases by 4. Remember, the mass number is a total number of protons and neutrons in a nucleus. So the mass number is all the protons and neutrons, and then an alpha particle has just been emitted from that nucleus, meaning 2 protons and 2 neutrons have gone. So now I've got 2 less protons and 2 less neutrons in my bundle. Shrinks a little bit because I've just lost 4 particles from it. So the mass goes down by 4. And an important feature there, a new element is formed. So that's alpha decay. By all means, pause the video to have a quick look at that. That's alpha decay. Okay, moving on then. So beta decay. So in beta decay, one of the neutrons in the nucleus decays into a proton and an electron. So you've got, let's say, for example, you've got carbon-15 here, ran its own business, unstable, and it decides one of the neutrons turns into a proton and an electron. Now, you're probably thinking, how is that even possible? Think about it. A neutron, by definition, is neutral. It's neutral. It can be made up of a proton and electron because if I add something that's got a +1 charge to something that's got a -1 charge and I stick them together, I've now got a neutral substance. So it is possible for a neutron to decay, to break down into a proton and an electron. What's interesting is, though, it doesn't just eject both of those two things. It keeps that proton, but ejects the electron. So what that actually does then, if you think about that in terms of atomic number and atomic mass and everything else, well, it started off with a certain number of neutrons and protons, and then the neutron decided, you know what, I'm going to be a proton instead and an electron. I'm going to turn into those two things. So the mass number stays the same because it's gone from a neutron into a proton and electron. Again, we're ignoring electrons when we're talking about mass. So it's gone from a neutron to a proton. Mass number doesn't change, but its atomic number changes because it's just turned a neutron into a proton. Its proton number's gone up. So in this situation, a new element's formed. Again, we've gone from carbon into nitrogen. Notice how carbon-15 is nitrogen-15. The mass hasn't changed. No change in mass. Okay, so let's look at this in detail then. So when a beta particle is formed, is emitted from a nucleus, the nucleus has got one more proton, so the atomic number increases by 1, hence the change in element. And the nucleus has one less neutron, but the mass number is unchanged because it's gone from a neutron into a proton. Both of those things contribute to the mass of the nucleus, so it doesn't change. A new element gets formed. Right, so the 2 questions here that I want you to have a go at. In figure 4.5, what are the differences between the nitrogen nucleus and the carbon nucleus? So have a look at them, have a think about what's happened. And then number 5 says, what happens to the nucleus when A, an alpha particle is emitted, and then B, a beta particle is emitted. So the way I want you to set this out is just like question 4, whatever the answer is, question 5A, whatever the answer is, question 5B, whatever the answer is, because I know that is written really poorly. It's not really indicated that there's 2 separate questions in one there. So pause the video. There's 3 questions there, let's say 3 minutes again. Don't overdo it, have a quick look, rewind the video if you need to, and then I'll go through the answers in a second. Okay, let's jump into those then. So For question 4, the question was, what are the differences between the nitrogen nucleus and the carbon nucleus? So the nitrogen nucleus's atomic number has increased by 1 compared to carbon, and its number of neutrons has decreased by 1, although the mass number stays the same. Okay, so you can see that the atomic number's gone up, but the atomic mass has stayed the same. Question 5 said, what happens to the nucleus when an alpha particle is emitted? During alpha decay, 2 protons and 2 neutrons are emitted from the nucleus. This decreases the atomic number by 2 and the atomic mass by 4. You might have also said that it creates a new element. That's fine as well. All of these create a new element that we've talked about so far, alpha and beta decay. And then question 5b says, what happens to the nucleus when a beta particle is emitted? So during beta decay, a neutron becomes a proton and electron. The electron gets emitted, but the proton is kind of withheld in the nucleus. This increases the atomic number by 1 and causes no change to the atomic mass. Because again, I've gone from one particle, I've converted one particle with a mass of 1 into another particle with a mass of 1. And again, don't let it confuse you. We're ignoring the electron because its mass is so negligible, it basically plays no part in this. So it's converted one particle with a mass of 1 into another particle with a mass of 1. So the mass essentially hasn't changed. The thing that has changed is the atomic number. Okay, so it went from a neutron into a proton, its atomic number has gone up, and therefore that changes the nucleus into the nucleus of a different element. It's not the same element as it was before beta decay. I'll leave that for a second if you want to have a quick look and pause it or whatever. Okay, so gamma decay then. It felt a bit weird putting questions before this. We've done alpha and beta, and then I went to questions on those two because there's not much to ask you about here, to be honest with you. So in gamma decay, gamma rays are emitted from a nucleus. These are really high energy electromagnetic waves, and they have no charge and no mass. So there's nothing to worry about in terms of, a neutron becomes a proton, an electron, none of that. The emission of gamma ray does not cause the mass or the charge of the nucleus to change. No protons are made, no neutrons and protons are given out, no electrons are given out, none of that. It's just a wave that is emitted from the nucleus of the atom. Okay, so there's some questions there that I want you to have a go at. I'm not going to give you a time on this. You take as much time as you want, basically. So pause this. The answers are coming, but do try and do it yourself. If you're going through the answers without really trying the questions yourself, you're not testing yourself. You're not learning to see. You're not checking to see if you actually understand whatever the topic's about. So just pause that. Take as long as you need to pause it. If you want to rewind. I don't mind you doing a bit of research on this. Like if you want to pause it and open up a new tab and go and do some research on it, by all means do that. Just don't jump straight to the answers until you've tried the questions yourself. So those are the questions. Just pause the video, give those a go. Okay, answers coming up. There they are. So ignore the worksheets 4.2. All that stuff. Just go off it. Question 1, question 2, question 3, question 4. Okay, so there's your answers. I won't go through them with you because it's self-explanatory. I'm not expecting you to have a green pen either, but there you go. So hopefully that's been helpful. As usual, any questions, drop them on the Google Classroom. Whichever teacher has put this up for you to do should be able to help you out. If I see it, I'll help you out as well, though. Yeah, hope that was useful. See you later.